Hello everybody, and welcome to our video part 1 on the hyperbola. So we'll start with the geometric definition of the hyperbola. It is the set of all points in the plane, the absolute value of the difference of whose distances from two fixed points is a constant. The fixed points are called the foci of the hyperbola. So that's a bit more of a mouthful than it really is conceptually. Let's try to break this down a little bit. What this says is if we take the two distances from any point on here to these two foci in blue on this graph, and we subtract them, and then take the absolute value just to make it positive, we will get the same value no matter which points we look at. So if I was to take, say, another point, how about over here, and do the same thing. And I took the two distances from that point P2 to each focus, and then I subtracted them and took the absolute value, I would get the same value that I did for that first point. So when we think about the hyperbola, just like with the ellipse and the parabola, it's going to be best to think about the geometric components here. So just if we take a quick look at this graph that we've got, we have the center here and we have two vertices for the hyperbola. And the distance from the center to each vertex is A. And the distance from the center to the foci is each C. And then we will also have a distance that corresponds to B, but we'll talk about that in a moment. All right, so as far as these labels are concerned, as we've been doing, F1 and F2 are foci, V1 and V2 are vertices, 0, 0 is the center. And we call the line between the two vertices the transverse axis. So that's this line here. And to restate the definition a little bit in mathematical notation, for any point P on the hyperbola, the absolute value of the distance from P to F1 minus the distance from P to F2 is equal to 2 times A, a constant. Well, how do we know that it's 2 times A? Well, it's similar to the reasoning for similar property on the ellipse. So let's just take a look at this graph that we drew real quick. So since this definition holds for any points on the graph, it also holds for the vertices. So if I take this first vertex here, the distance from that vertex to the F2 is this yellow line. And if I subtract the distance to F1 here, what I've really done is canceled out this part here by subtracting that green part, and the distance that's left over is 2A. Alright, so that value is always 2A, and that'll come up in some application problems. Alright, now here we go. We've got our equations of a hyperbola with center 0, 0. So this is a little bit different than the equation of the ellipse, I should say. The hyperbola looks like I made a little typo here. Let's go ahead and fix that. That should be hyperbola. That was a silly typo. All right, well, the rest of this should be correct, so no worries there. All right, so we get subtraction instead of addition when we look at the equation of the hyperbolas. Now, these equations are derived pretty much the same way that the ellipse and the parabola equation is derived, But like the ellipse, the algebraic manipulations are pretty convoluted. It's just a bit too cumbersome, so we're going to go ahead and skip that. But we get something very similar to the equation of the ellipse. And we're going to think about it the same sort of way. So we have this chart here of all of the parts of the hyperbola, and it's useful maybe as a reference, just like the others, but not really much that you want to focus on. So the only things I want to point out is that the relationship of A, B, and C for the hyperbola is different than that of the ellipse. C squared equals A squared plus B squared. And this does look like the Pythagorean theorem. Of course, A, B, and C aren't actually the sides of a right triangle, so it's not really the Pythagorean theorem, but it sure does look like it. And the other key difference I want to point out is that when it comes to hyperbolas, A is always paired with the positive term, and B is paired with the negative term. So whichever term is positive decides which your main axis is, your transverse axis. So in this case, x squared is positive, so the main axis is along the x-axis. And in the case of the vertical hyperbola, y squared is the positive term, and so your main axis is along the y-axis. And that's the main things that we want to think about geometrically when it comes to the hyperbola, graphing them and working on their equations. So let's take a look at a key property of the hyperbola that we'll use to graph these quite a bit more accurately. So it's a little bit of an odd thing here. So we think about this graph. These hyperbolas, they have what are called diagonal asymptotes. If you look, it kind of looks like this graph just eventually starts shaping out like a straight line towards the end. And that's what we're going to look at now, and we're going to look at that a bit more rigorously. So, the diagonal asymptotes of the hyperbola. So we're going to look at the horizontal case. This is two different situations here. So in the horizontal case, our equation would be x squared over a squared minus y squared over b squared equals 1. And so what we're going to do is rearrange this equation a bit and solve for y. So we move y squared over b squared to the right-hand side and then move 1 to the left, and we get x squared over a squared minus 1 equals y squared over b squared. And then we're going to multiply b squared across and then just rearrange here, put y squared on the left side. So we get y squared equals b squared over a squared times x squared minus 1. And so y is equal to plus or minus the square root of b squared over a squared times x squared minus 1. And then to use the terminology of limits here, as x approaches infinity, what's happening here? Well, inside this square root, this term, b squared over a squared times x squared, is going to get huge when x goes to infinity. So this negative 1 becomes almost completely irrelevant, right? When x starts getting to like 10, 20, 30, 50, 100, that negative 1 makes very little difference in the value of y that we're getting. So what we can say is for large values of x, that y is approximately the same thing as the square root of plus or minus the square root of b squared over a squared times x squared. In other words, y is approximately plus or minus b over a times x. So that is to say that for large values of x, we're really just looking at the behavior of two lines, y equals b over ax and y equals negative b over ax. As x gets large, the function starts to behave like these two lines. And as you can see on this graph, we would have two diagonal lines that describe that behavior for extreme x values. And we can work through the same logic in the vertical case. Now, I'm not going to do the play-by-play again, but what you'll see is that since we have y squared divided by a squared here, that when we solve everything out, we actually get y is approximately plus or minus a over bx instead of b over a. So it depends which case you have, the horizontal or vertical case, which formula you get for these asymptotic lines, these diagonal asymptotes. So let's take a look at this in the context of a basic graph. So here we have the horizontal graph x squared over a squared minus y squared over b squared equals 1. So our vertices occur at, we're centered at 0, 0, so our vertices occur at a0 and negative a0. And if we go up a distance of b on the y-axis, which is our minor axis, and down a distance of b, we get this rectangle here that we can draw using the vertices and these minor endpoints here. And we call this rectangle the fundamental rectangle of the hyperbola. And the reason we call it that is because if you notice, the distance here up to this line is b and over is a. That means the slope of this line passing through the diagonals is b over a. That's y equals b over ax. And likewise, the slope of the line passing through the other two diagonals is y equals negative b over ax. So by drawing the fundamental rectangle, we have our position for our vertices, and we know what our asymptotic behavior will look like, and then this graph in purple will be our hyperbola. So we can actually get a very good idea of the behavior of the hyperbola when we draw our graphs by first using this fundamental rectangle. So I'm going to pretty consistently rely on this fundamental rectangle when I graph these hyperbolas. Similarly, I want to point out here, when we look at the vertical hyperbola, our vertices are at 0a and 0 negative a. We go out from our center a distance of a in the vertical direction. And we go out to a distance of b in the horizontal. And so what we see again is that this time our rise is a and our run is b. And so our slope is a over b, or negative a over b. So we get the asymptotic lines, y equals a over bx, or y equals a over negative a over bx. All right, well, let's try to put some of this information to use. All right, so a equals 2, b equals 3 here. Remember, a pairs up with the positive term in hyperbolas. So since our positive term is y squared, a is 2 here, and this is also going to be a vertical hyperbola. And when we graph, we want to graph the vertices, the foci, the fundamental rectangle, and the graph itself. So let's go ahead and do that. Now I do want to find c. So remember, in this case, c squared is actually a squared plus b squared. So let's go ahead and solve it. C squared is 4 plus 9. Well, let's write that out fully. C squared is a squared plus b squared. So c squared is 4 plus 9, which is 13. So c is the square root of 13. So that makes c a little bit bigger than 3 and a little bit smaller than 4. All right, so let's go ahead and plot all of this information. So remember, our center here is 0, 0. And so our vertices are going to go out a distance of A on the vertical. So that's up to here, that's V1, which is 0, 2, and V2, which is 0, negative 2. And just, I want to reiterate one more time, A goes with the positive term here. So whereas in ellipses, A was always the larger number, that's not the case for hyperbolas. B can be larger. A is just whichever one goes with the positive term. All right, and now for the minor axis of our fundamental rectangle, all right, that's B is going to be 3. So we go out to here and out to here. So our fundamental rectangle is going to look like this. And let's go ahead and graph our foci as well. So they're going to be roughly here, F1, which is going to be at 0, the square root of 13, and F2, which is going to be down here, at 0, negative the square root of 13. I'm going to draw my diagonal asymptotes. And the great thing is I don't have to memorize a bunch of formulas to know what my diagonal asymptotes are. That's the beauty of the fundamental rectangle, is I can just look at my rise, which is 2, over my run, which is 3, and say, hey, this is y equals rise over run, that's 2/3 x. And this other one is y equals negative that. And now when I go to actually graph my equation, which we'll do in this green color here, we'll just start out from our vertices, we'll curve outwards. And then as we approach this diagonal, it'll kind of level off. It's not a perfect picture, but as long as it gets the idea across. All right, well, we've graphed this hyperbola. Okay, so now we're going to find and plot the vertices, the foci, the transverse axis of the hyperbola, state how the hyperbola opens, find and plot the vertices of the fundamental rectangle, sketch the asymptotes and write their equations, graph the hyperbola. This is all the same stuff we were doing before, just laying it all out explicitly. Now, of course, here we've got a slightly different equation. We've got 9x squared minus y squared equals 36. This thing needs to be equal to 1, so we're just going to start out by dividing both sides by 36. That gives me x squared over 4 minus y squared over 36 equals 1. And this is a horizontal hyperbola because the x squared term is positive. So now we'll go ahead and we'll start graphing our information. We've got the a equals 2, b equals 6. Well, and let's go ahead and find c. Well, c squared equals a squared plus b squared. So c squared is 4 plus 36. C squared is 40. C is the square root of 40. So since it's horizontal, we'll start at our center, 0, 0. And we'll go out a distance of a, which is 2. And that'll give us our vertex 1, which will be at 2, 0. And vertex 2, which will be at negative 2, 0. So the transverse axis here is going to be the x-axis. which we could say highlight here since it does ask us to quote-unquote plot it. How does this open? Well, we already said that it's horizontal. We've found the vertices of the regular vertices. Now we got to find the minor vertices of the fundamental rectangle. So since b is 6, we're going to go up 6 in each direction here. So up 6 and down. So we could call this M1 is 0, -6, and M2 is 0, +6. Now let's go ahead and draw ourselves a fundamental rectangle. Alright, so that's our fundamental rectangle. Let's sketch the asymptotes. They're just going to go through the corners of the rectangle and the center of the graph, or center of the plane, I should say. Oh, a little glitch there. Let's try that again. And let's see what these equations are. Well, this is y equals my rise for my rectangle. I'm going up 6 and over 2. So that's 6 over 2x, which is, of course, just 3x. And for the other diagonal here, I would have y equals -3x. So those are the asymptotes. And finally, we can graph the actual hyperbola. We started our vertices. We curve outwards towards our asymptote. This one's very elongated. Close enough. All right, well, that one was a very stretched out hyperbola. All right, let's go ahead and take a look at another example. Find an equation of the hyperbola satisfying the given conditions. Graph the hyperbola. So in this case, we've got vertices given and foci given. So let's just go ahead and plot those and figure out what it tells us. So both of these are on the x-axis, of course, right? Because the vertices are always on the same axis as the foci. So V1 here is at 3, 0. V2 is at -3, 0. And let's plot the foci. That's F1 is at 5, 0. F2 is at -5, 0. And what does this tell me? This tells me that A is 3 and C is 5. And so C squared equals A squared plus B squared tells me that 25 equals 9 plus B squared. That means B squared is 16, and therefore B is 4. So that tells me if I want to plot the other endpoints of the fundamental rectangle, I just need to go out 4 in each direction from my center. Now I already have everything that I need since I have B and I have A to find the equation, but I'm so close to being done graphing, I'm just going to finish that first. So I've plotted my fundamental rectangle and my asymptotes. It doesn't ask me for the details on them, so I'm not going to bother writing them down, but I'll draw out my hyperbola here in purple, right, curving outwards towards my asymptotes. The picture's not perfect, but it's close enough. Now, this is horizontal, and that tells us that the equation should look like x squared over a squared minus y squared over b squared equals 1. And therefore x squared over 9 minus y squared over 16 should be equal to 1. All right, we got one last example here. Find an equation of the hyperbola satisfying the given conditions. Graph the hyperbola. So we're given the vertices, plus or minus 3, and asymptotes, y equals plus or minus 2x. Now, when these asymptotes are given, they're not going to be given in terms of a and b directly. It's usually going to be like a simplified number, so you have to work out the reasoning just a little bit. So let's plot our vertices. So I get 3, 0, and negative 3, 0. Now, if my slope is 2, then by the time my x value has reached 3 over here, then my diagonal asymptote would have to reach 6. Right? Since we're looking at a line with slope 2, when x is 3, y would be 6. So that tells me what b is. So if I just plot my fundamental rectangle now, so it's not perfectly to scale. That's okay. All right, so now I know what A is. A is my distance out to my vertex. B is my distance up on the fundamental rectangle. So A is 3, B is 6. And based on my vertices here, my hyperbola opens right, or opens horizontally, I should say. And I could draw my diagonals. I've run out of room here. I'm not too concerned about that. Let's go ahead and find the equation, though. So since this is horizontal, it'll be x squared over a squared minus y squared over b squared equals 1. Which tells me it's x squared over 9 minus y squared over 16 is 1. So these are just different ways of taking the information that you're given and deducing everything you need to know about the hyperbola from that. All right, well, that's the end of part 1. Thank you for watching.